Okay, 3.2. So last time we noted that our exponential functions were one-to-one and therefore invertible. What is the inverse then? Well, it turns out to be the logarithmic function. And that's what we're going to talk about in 3.2. Okay. So, first off, to define these things, and we recall how our inverse, finding inverses works. So if you had f of x equals 3x plus 1, and this thing is one-to-one and invertible, then we could swap the x and the y, so you have 3y plus 1 now, and then solve for y. So you have 3y equals x minus 1, and then divide both sides by 3, so y equals x minus 1 over 3, and that'd be your inverse function. Okay? So in this case, f inverse of x would equal x minus 1 over 3. We want to do the same thing with natural logs. So now consider then f of x equals b to the x, right? And we hope we can do the same thing. We want to go, all right, let's swap the x and the y. So x is equal to b to the y. And then we try to solve this thing. So the problem is we don't really quite know how to get that y out of the exponent. You know, we square both sides. What am I going to do? I don't know. The y-th root, maybe? I don't know. So at the end of the day, what we're just going to do is define the thing. It's kind of like when we define radical negative 1 to be I. It's the same sort of idea. So now we're going to define y to be this logarithm thing. So we'll say y is equal to log base b of x. Okay. So in general then, you'll see this definition in the book, y equals log base b of x, if and only if b to the y equals x. Okay. So we'll use this definition in the beginning to just evaluate some questions. So first we're going from log form to exponential form, and this is problem 2. We have 6 equals, I don't know if the page there, sorry. 6 equals log base 2 of 64. Okay. So we can rewrite this using this transformation. I'll say b to the y equals x. So 2 to the 6 equals 64. And it's one of these things you're just going to have to practice, and after a while it'll be second nature. Okay. Let's look at another, number 8. Log base 5 of 125 equals y. So we can rewrite it, 5 to the y equals 125. Okay, let's practice converting in the other direction, exponential to logarithm. So problem 10, we have 5 to the 4th equals 625. Okay, so I go log, and the base 5, 5 to the 4 power equals 625. Let's try another one, 14. So 14, they'll try to trick you a little by putting the exponent in the form of a root. Okay. So we can rewrite it as 64 to the 1/3 power equals 4. And then we're basically filling in the boxes here, right? So the base is 64. And then we're raising it to the 1/3 power, so that goes up there, and then that equals 4. Okay. So once you get the handle on this, you're able to actually evaluate logs. you can put it in terms of an exponential expression and ask yourself, for example, number 8, I want to know what log base 5 of 125 is. Well, what you're really doing is asking 5 to what power equals 125. So you can evaluate these guys by doing this transformation in your head and solving accordingly. So you're asking 5 to what power is 125? 3. So log base 5 of 125 is 3. Okay, so I have a bunch of mini exercises in the book we'll go through and take a look at. So section 2, evaluating logs. So if you see something like log base 2 of 16, you're asking 2 to what power equals 16. And obviously this is not always going to work. You have to use a calculator for some of them, like log base 2 of 5. 2 to what power equals 5? I have no idea. But for for this kind of problem, you should be able to do it without a calculator. 2 to what power is 16? Well, 2 times 2 is 4, times 2 is 8, times 2, 16. 2 to the 4th power. So this would equal 4. Okay, so let's investigate some of the problems in the book then. So 22, log base 7 of 49. 28, log base 3 of 1/9. So the first one, 7 to what power is 49? Well, 7 squared is 49. So log base 7 of 49 is 2. 3 to what power equals 1/9? Well, we can rewrite 1/9 as 1 all over 3 squared. And then our rules of exponents, sorry, I went off the page again. 1 over 9 is 1 over 3 squared. The rules of exponents say you can rewrite this as 3 to the negative 2. Okay? So it must be that 3 to the negative 2 is equal to 1/9. Okay, well, let's keep going. 30. Log base 6 of the square root of 6. So here again, they're trying to trick you with these radical expressions, but in reality, you can always rewrite it as a fraction exponent. So 6 to what power equals 6 to the 1/2? Well, that's easy. That's just 1/2. And you can think through these in your head now. 3 to what power is 1 over radical 3? That'll be negative 1/2. If you don't see that, you can always try to rewrite it a little bit. This is the same as 1 over 3 to the 1/2. And that's equal to log base 3 of 3 to the negative 1/2. And then it's quite clear. 3 to what power is 3 to the negative 1/2? Well, negative 1/2. (34) log base 81 of 9. So 81 to what power is 9? Well, if you took the square root of 81, that would give you 9. So it's 1/2. 35, log base 11 of 11. Okay, so 11 to what power is 11? Well, that's just 1. And then another one, so this one is kind of a common guy that you see, log of the base is equal to 1. The other one that's kind of common is this one, 38, log base 6 of 1. So the log of 1 is always going to be 0, okay, because you're taking a base and raising it to 0 power, and that'll give you the 1 inside the log. So in general, you could say log base b of 1 will always equal 0. Okay, so that in mind, we can continue on with that and say, all right, there's some basic properties going on here, right? So section 3, the basic properties. And 1 is 35, the property we're seeing in 35. So if you have log base b of b, that's just going to be 1. Right? And then property number 2 is from 38, and it's just this property here. So log base b of 1 is always 0. Right? And then there's the cancellation equations from working with inverse functions give us some formulas to work with. So if you have f of f inverse of x, you get x back. It turns into the identity function. Okay? So in this case, if you have log base b, and then you put b to the x inside of it, you just get back x. And we saw that phenomenon as we worked through some of these exercises. For example, 30, log base b of 6 to the x, basically, gives you x. So you can think of it as all these things cancel out. The log and the 6 here cancel. Log base 6 and 6 all cancel out, and you're just left with the exponent, 1/2. Related to this then is the other version of the cancellation equations, f inverse of f of x equals x. And so if you take a base b and you raise it to the log base b of x, you're going to end up with x again. So you're putting the logarithm inside the exponential. Here you're putting the exponential inside of the logarithm. Okay? And they sort of just have a way of canceling themselves out, and you just are left over with the input. Okay, the next section then is on graphing these characters. So we want to be able to graph them. We'll do it just like before. Take a look at the graphs using point plotting, and then we'll talk about the characteristics of the graphs, their range, domain, intercepts, asymptotes, and then we'll talk about plotting them with translations. Okay, so section 4, graphs of logs. And we'll look at checkpoint 6. So in particular, we have f of x equaling 3 to the x. And we want to graph, well, this isn't how are these going to work? We're using the exponential to graph the logarithm. Okay, so if you were given initially, so I kind of did it backwards. If you're initially given log base 3 of x, the way you want to graph that thing is to graph this thing and then revolve it around the line y equals x. Okay, so we start out with this thing right here. Okay, so I can go -2, -1, 0, 1, 2. This will be f of x. So putting -2 into this 3 to the -2 is the same as 1 over 3 squared, in other words, 1/9. 3 to the -1 is the same as 1 over 3. 3 to the 0 is the same as 1. 3 to the 1 is the same as 3. 3 squared is the same as 9. Okay? So you can, eventually we're going to zip over here and graph it. Let's see what we have so far. 2, 1, 2. So -2. I want to go 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so -2, 1/9, -1, 1/3, 0, 1, 1, 3, and then 2, 9. So the way we can get the graph of the logarithm then is to rotate this graph around the line y equals x, okay, which is just the diagonal through the origin. I'm going to need a lot more room. I'm going to have to smush it a little bit. Sorry about that. Okay, so you can do this visually, and that'll work. It may be easier to just reverse all the x and y coordinates to get the new graph, though. So for g of x, so essentially the same thing. To rotate this around the line y equals x, which is this line I just drew in blue, to accomplish that, it's exactly the same as just taking all of these coordinates and flipping them. In other words, plot the points 1/9, -2, 1/3, -1, 1, 0, 3, 1, 9, 2. And you'll have the inverse graph. Right? So you see I just took this one, this y value, made it the new x value, took the y, Okay, hopefully that's obvious. Right, so 1/9, -2. 1/3, -1. 1, 0. 3, 1, 2, 3, 1. And then 9, 2. Okay. And you connect the dots on those and you should have your inverse. And it should look as though you took this graph and just copied and pasted it on the other side of this diagonal. Okay, so that's the standard way of drawing these things. Let's take a look at the characteristics. So section 5 then, characteristics of the graph. First off, the domain and range are going to be the opposite of the domain and range for the exponential. So the exponential's domain was -∞ to infinity. So the range of the logarithm is going to be -∞ to infinity. And we can see that on this graph. If we were to smush this thing onto the y-axis, the pink graph onto the y-axis, it would go from -∞ to infinity. The remnants would be on the y-axis. The domain then is going to go from 0 to infinity, which is the range of the exponential. Okay. Thirdly then, instead of a y-intercept, it's going to have an x-intercept. So for the exponential, it had the point 0, 1, so we'll have 1, 0 as our x-intercept. Okay. Similarly, we could talk about forms here. So the form when the b value is greater than 1 will be this form. And then the form when the b value is in between 0 and 1 will be this form. And how did I get that? Well, you're going to rotate this one about the well, the line y equals x, I believe. Okay, so I mean, if you look at the exponential decay and then rotate that, you'll get this graph here. Okay, so again, I'm using this idea. If I just graph the exponential form, so in this case, if b is in between 0 and 1, this guy, this will be this dashed line here, will be the decay, exponential decay version going down. Just like over here, the inverse is the exponential growth function, y equals b to the x in that case. And then if you rotated that around that diagonal, you would get this logarithmic form where the b value is greater than 1. Then if you have the b value between 0 and 1, you have the decay form of the exponential. And if you rotated that about the line y equals x, you get this graph here, this logarithmic graph where b is between 0 and 1. Okay. There's a vertical asymptote now instead of the horizontal asymptote. So the horizontal asymptote for the exponential function is y equals 0. And then the vertical asymptote for the logarithm function is x equals 0. So we have a vertical asymptote. X equals 0. Okay, and again, it's going to be obscured because of the y-axis, but when we go to translations and start moving around, you're going to see the asymptote is going to be kind of attached to the exponential function. Okay, let's talk about graphing by translations then. And again, let's just go through all of the different types of translations, starting with vertical. So if you have y equals log base b of x plus or minus c, you're either going up or down. Horizontal, you'll have y equals log base b of x plus or minus c. That'll move you left or right. Then we have our rotations. So if you have y equals log base b of negative x, that'll rotate you about the y-axis. If you have y equals negative log base b of x, that'll give you an x-axis rotation. And then finally, if you have, we have the vertical stretches and shrinks, which I'm not, it's these three I'm always worried about for the test, but the other ones, stretch, shrink. So for the horizontal version of this, you're thinking in terms, if this is a trig class, that would be your period. And so you're manipulating the guts, so to speak, of the logarithm. If c is in between 0 and 1, that'll give you a stretch. If c is greater than 1, that's going to cause a shrink. Right? Then you'll have your vertical version, where you're multiplying the outside of the log by some constant, and that's kind of the idea here is it's an amplitude idea. So it's going to stretch it. If c is greater than 1, it's a stretch this time. And then it'll shrink if c is in between 0 and 1. Okay? Okay. So let's take a look at least one of these. And when you do these in your homework, one thing I'll look for is whether or not you're indicating what happened to the asymptote at the end of the day. So we'll have, anyways, g of x is log base 2 of x plus 2. And what we'll do first is graph log base 2 of x. Okay? In order to get log base 2 of x, I'm going to graph y equals 2 to the x. And then rotate the x and y coordinates. Okay? So again, I'll go with negative 2 to 2. Okay, so plugging that into here, 2 to the negative 2 is 1/4. 2 to the negative 1 is 1/2. 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. So y equaling log base 2 of x, that's going to give us 1/4 comma negative 2, 1/2 comma negative 1, 1, 0, 2, 1, 4, 2. Okay, so let's go ahead and try it now. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 3, 4. 1/4 negative 2. 1/2 negative 1. 1, 0. 2, 1. And then 4. 1, 2, 3, 4, 1, 2. Okay, so our sort of first original graph is there. Then I want to draw the shifted version and manipulating the insides. That means it's a horizontal shift, and we're going x plus 2, so we're going to the left. So each of these coordinates is going to go over 1, 2 points. Okay, so 1, 2. I'll put this guy in pink. Actually going to need a little bit more room there. Okay, so 1, 2, and 1, 2, and 1, 2, and 1, 2, and 1, 2. Okay. Try to make it as smooth as possible. That's going over in that direction. So the one thing that I'll be looking for in your homework is kind of the one detail, and I'll take off a point if you don't show it, is the change of the asymptote. So right now, although we don't see it, the asymptote is going through the y-axis. It's at x equals 0. So when you move this whole thing over 2 places, the asymptote is going to also move 2 places. We go over 1 and then 2 right here. Okay. So again, the graph isn't just about the things you see, it's about the things you don't see. And that is a fairly important factor because this logarithm is not going to keep going to the side like that. It's going to level off at -2. Okay. Okay. One new thing about these logarithms is the domain issue. Right? So let's see if I can find where we started with that. Yeah. So polynomials domains -infinity to infinity, right? Exponentials domains -infinity to infinity. There's no issues there. But you start talking about square root domains, so then you have to make sure everything in the root is greater than or equal to 0. Rational functions, we had to watch out for division by 0 in the denominator. Logarithms turn out to be another issue. So when you're defining your domains now, you're going to have to say the domain of the function is all real numbers except where there's division by 0, negatives under the radicals, or anything less than or equal to 0 in the logs. Okay, so it's just another thing to remember, I guess. Section 7, the domain of the log. So given your logarithmic function, f of x equals log base b of some object, we'll say it's g of x, so it could be like log base b of x minus 2 or log base b of x squared minus 1. If you're given this function, we need to ensure that g of x is strictly greater than 0. Okay? So before, a similar problem, given f of x equals the square root of g of x, we would have said that we need for g of x, the guts of that radical, to be greater than or equal to 0. Okay? Likewise, given f of x equals g of x all over h of x, what did we need there? We need for h of x to not be equal to 0. Okay? So it's just along those lines. We've sort of dealt with these issues before. Now we're just going to have an extra issue whenever you see logarithms. You have more work to do. Okay, so let's look at 76. And we're trying to figure out the domain of this thing. We have f of x equaling log base b, or log base 5, excuse me, of x plus 6. So I need to take x plus 6 and make sure it's greater than 0 for the domain. So x plus 6 needs to be greater than 0. Subtract 6 from both sides. So you need x to be greater than -6. So the domain in interval notation, -6 to infinity. Okay. Let's look at another one, number 80. This one's a little harder and relies on some of the stuff that we were doing in the previous chapter. F of x equals ln of x minus 7 squared. Okay. So we need to make sure that x minus 7 squared is greater than 0. This is a polynomial inequality, and we learned how to solve these in the last section. So we need to find the boundary points. It's already in the appropriate form. We have polynomial inequality and then 0 on the other side. So I need to find the boundary points, set it equal to 0, so x equals 7. And then I need to determine the solution interval using the number lines. So we have test values, we have the signs, and we have the conclusion. Okay, so I'll try x equals 0. Plugging that in here, I have negative times a negative is positive, it's greater than, so that's our solution interval. Let's try x equals 8. If I put that in there, it'll be positive times positive, which is also positive. Okay, so it'll be greater than 0. In other words, we have two solution intervals. We do not include 7, so use an open dot there because of the inequality type. And the open dot implies that in our symbols we need to use parentheses. So our intervals that work, -infinity to 7, And then we have a hole at 7, and then we go from 7 to infinity. Okay, so that one's a little harder. Let's finally, in the end, we look at more specific logarithms that come up in applications that we use primarily. We don't really fool around with log base 7 or log base 20 very much. So in particular, there's two types of logs we look at, the common and the natural log. Okay. So the common log, first off, is log base 10. So log base 10, like 10 counting fingers. We will not write it with the base. We'll just write log of x. That's how common it is. So for example, 82, we have log of 1,000. And so you're asking yourself, 10 to what power is 1,000? And that, of course, is 3. The next kind of log is the natural log. And this is log base e. Okay, so instead of writing log base e of x, you're going to write ln of x. Okay, so they'll have problems associated with this. Let's look at a couple. The natural log of e. Okay, so this is asking log base e of e. In other words, e to what power is e? And that's just going to be 1. Number 90, the natural log of e to the 7th. Okay, so log base e of e to the 7th. That's just going to be 7. 87, the natural log of 1. So e to what power is 1? That's 0. And then 94, e to the ln of 300. This is one of the cancellation equation forms. The exponential, the base e and the logarithm will kind of cancel each other out, and you'll just be left with 300. Okay, so that's this section.